Alright guys, I'm back with another video and I'm going to be doing this problem. I'm going to be explaining it. And I really like this question. This is actually from a recent Div 2 contest. It's called Trees and Segments and it is a pretty difficult problem. The rating is like 2200, but I think it's actually pretty doable because what I really want to focus on this problem is not necessarily how to do it. I think the editorial is actually pretty fine. There's like one unclear part to me when I was looking at the editorial, but like I figured it out myself. So I think the editorial actually is pretty fine. But of course, the editorial never like tells you how to like motivate the solution or how to like come up with a stream of thought that would lead to the solution. Like continuous thoughts that will like lead to the solution, right? That's sort of what you have to find yourself. And I thought I did a pretty good job finding that for this problem, and I want to like reinforce those ideas. So anytime I do a good problem, I like making a video because it reinforces those ideas, and like also making videos is a hobby at this point for me. Um, so I think the problem is pretty straightforward, like what it's asking. But there's something that I really want to focus that really motivates the solution. It's this idea of fixing parameters in problems. This will make sense when we actually delve into the solution. But just to preface this before we go into it, like a like the idea of fixing is like not really like explicitly like mentioned in solutions, or like people don't really like call it like a method. But it's just the idea that when you fix a certain parameter of the problem or you add conditions to a problem, like for example, like a very simple idea of this is binary search. You're saying, let's fix the answer to this problem as X and let's see if this answer is achievable. When you fix that parameter, you're solving a different form of the same question, and that form is more approachable, it's more doable, because now that you're fixing a parameter, you can add a layer of direction to your thoughts. You can now make conscious thoughts based off of that fixed parameter. So this seems very abstract, but I see this in countless of problems. It doesn't matter if it's like a very easy problem or a very difficult problem. Like a lot of problems have the same theme of like sort of fixing certain parameters to make the problem easier, right? And like I said, the most typical application of this is binary search. But even in this problem, you can fix something that will make it easier. So let's just talk about how this is sort of applied to trees and segments. Now, of course, there is some dynamic programming, which I'm going to actually now suggest that the dynamic programming is secondary to this problem. Like it's a very secondary thing. Like this is not a DP problem. This is a DP problem, but I feel like you don't have to have the mindset that like DP is the main focus. You can just say, oh, I came to this solution, now I need to find, and I want to use DP to do this pretty standard thing. Like the DP is like honestly pretty standard. Like it's not too hard to like I think of, in my opinion. It, but the motivation behind the DP is hard. That's what makes this hard. So, anyways, enough yapping. We're gonna get right into the problem. So, how do we even approach this problem? This is a very interesting one. I really like it. So, the idea here is that we basically like what the question is saying is we have a string of ones and zeros, and the idea here is that L0 represents the maximum contiguous segment of zeros, and L1 represents the maximum contiguous segment of ones. And apparently there's just some expression that says that the beauty of the string is considered as A times L0 plus L1. And the idea is that we can flip, and to flip a bit means you change 1 to 0 and vice versa, right? So the idea is that we're going to be able to flip no more than k bits, and we want to maximize this expression for values of a from 1 to n. Notice that the algorithm to solve query 1, to solve a equals 1 is the same thing as a equals 2. Like, obviously you would want L0 to be greater than L1 intuitively, because like it has that coefficient which is not 1. So like it's pretty much like you obviously, for example, like I would want 10 here, right? To make this, more. If I had like 5, like I would like I you know what I'm saying? So, or like I wouldn't want to switch 5 and 6, right? So it's just sort of kind of intuitive common sense type of stuff. But like just notice that the query is like the algorithm to solve like a equals 1 is the exact same to solve a equals 2. So it's a little bit weird, like kind of. I guess it's sort of. Yeah, at first it seems like a little bit weird. It's just like what's the point of these a values? But anyways, um, one thing you can think about. So again, you should go through the test cases. Um, you can just look at the test cases. To be honest, that's what you can do if you want to. But again, we're going to just assume, without loss of generality, that a is equal to 1, because it doesn't like I said, it doesn't like the algorithm is going to be the same, right? Like just find an algorithm for a equals 1, right? Let's find an algorithm for a equals 1, and this won't lose any generality because we can still generalize the a equal 1 case to anything. So that's what I'm saying, without loss of generality, right? So without loss of generality, we can say we can assume a is equal 1, and then there is that maximize L0 plus L1. Now, the first thing when you're thinking about problems, you want to think about like what certain parameters are making this problem difficult. And usually those parameters, like it's if a parameter is making the problem difficult, then fix it. Like literally fix the value of a parameter. So you're like, oh, this value is fixed. And what I mean by this is that think about what we're doing. We're saying because we have no more than k changes, right? So let's say we have some random string like 1 0. What I really want to focus on, we might have some string like 1 0, and there's some like other parts of the string, right? These dots, these are like this is a part of the string, right? So this is like a whole string, but I'm just gonna focus on here. The idea is that we have no more than k changes. So what happens when we change a bit? Well, like why would we want to change a bit in the first place, right? Why would we want to flip a bit or like invert it, right? If I flip this 1, you might want to make you might flip that 1 to a 0 because you want to maximize L1, right? Like so like motivation behind changing a bit, changing from 1 to 0 to 1 is to possibly maximize the value of L1. Basically L1. And same with L0. Changing possibly maximize. That's what you would do. That's pretty much what you would do. Is the reason why we would want to change a bit in the first place. So we're just understanding like the underlying like problem here is why do we have these changes is because changing 1 could maximize the other, and changing 0 to 1 could it's that idea. Now here's what should be like here's why this problem is hard, because if you change 1, if you do a change, if you apply a change, it could possibly minimize the other one, right? So what I'm saying is that here when you apply a change, while it could maximize either L0, 1, it would in return possibly minimize the one it possibly maximized. So this is like kind of hold up, let me get my charger. So what this means is this is pretty confusing, but what I'm saying is that think about it like this, right? When we change 0 to 1, right? Like while that possibly could maximize L1, we possibly could minimize L0. Like maybe there's some zeros that were like really, 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 really long, and now you know, or like let's say this one was not here. There's some zeros that were really, really, really long, and if you change that to 1, well then while you could have maximized L1, you just minimized, L0. So that's what that's basically what I'm implying. I'm saying that it's not obvious, like when we're at each bit, like changing something to a 1 could possibly, we really don't know what to change because like if you change something to 1, okay, it can maximize L1 possibly, but then it can also minimize L0. If you change something to 0, it can possibly maximize L0, but then minimize L1. So it's the idea that there are competing effects. Like this is common in a lot of maximization problems, just in general. If you generally think about it, is increasing one parameter. It's not so obvious on how to maximize, let's say, a function or something, is because increasing one parameter decreases another parameter, and it's like weird because you need both of these parameters to be high in general to have a high result. And so it's like, shoot, what do we do? There's no sense of direction in which parameter we should do and like which bit we should change, and that becomes unobvious. So what is making this problem difficult is that there is no sense of direction of what bit we should change, right? That is the problem. Like fundamentally is that there's no, the underlying difficulty is that we have no idea um, if we should keep a bit or invert it. And more specifically, we don't know if we should change it to 0 to change it to 1. So the idea here is that the idea is that it's weird because we have two things to maximize, but they compete with each other, right? So basically, what we have to do is let's just let me erase this nonsense, okay? Because I really wanted to say like what because also like being very clear and very clear with your thoughts and like saying like what is this is the difficulty and this is how I'm going to solve it. So the difficulty is that we try to maximize L0 and L1, but maximizing one could minimize the other. So the big question is now what do we do? And this is what I'm talking about. This is and so maybe this seems like, 'cause this is not contrived. I feel like this is like a very motivated step. The answer to this question is definitely motivated. It's like we try to maximize L0 and we try to but maximizing one could minimize the other. So the question is now what do we do? We fix the value of either one. It doesn't matter. We fix the value of either L0 or L1. That's the idea. Don't you think that's fascinating, right? The idea is that this question motivates it because we're saying that, okay, if we fix the value of L0 or L1, then the idea is that now we know. Let's assume we fix the value of L0. What this allows us to do is now we know the value of L1 is fixed. So then when now after the value of L1 is fixed, you'll know, you have a sense of direction, right? Because we said the underlying difficulties, we have no idea if we should keep or a bit or invert it. Well, obviously, if you're going to change a bit, you obviously always change it to a 0 because L1 is already fixed. So the only thing you have left to do is to maximize the value of L0. That's the only thing you have left to do because the value of L1 is fixed. So in order to fix, so then it basically becomes, it basically becomes like L0 plus some constant. And to maximize this, we obviously just maximize L0. And so that's the idea, is that C is fixed now. L1 is just a constant. We're fixing it. It's not going to change. So the idea is that the question now has a sense of direction to it, has more focus. We know we are now given some changes, and we have to maximize L0. And this is for a fixed possible L1. Oh, this is a very bad thing that I didn't start out in the problem, which I probably should have. This is like really, really bad. Is notice that n is only, I don't know why I always forget this. N is 3000, so like possible solutions. I'll like put this on the side. Read constraints, but possible solutions. So like n squared. We're looking for like an n squared solution. N squared type solution. Or n squared log n, right? Whatever. But we know that L1 L1 is restricted. It has a bound, right? L1 is bounded from 1 to n. So we know we can certainly fix this value to be either one of them. And then now we can just think about this problem when L1 is already given to us. And so the thing is, like, how do we like particularly fix L1? Because that still seems pretty vague. So we know we're going to fix L1, but how does this look like? How does this work though? So if I fix the value to be L1, then the idea is that you're going to need to make some segment. So some LR segment, we're given that R minus L plus 1, that's equal to 0. You're going to have to make, you have to make sure that like every segment is just a bunch of ones. So this means that this is fixed. So this is like fixed, right? Because if I fix the value, and for L1, there are like so this is basically what I mean. So more specifically, because you want to be a little bit more specific, right? On like if you can be more specificity is always good. Um, uh, yeah. So more specifically, you're going to uh, fix a certain window of a certain window LR to be fully ones. That's what we're gonna do. More specifically, we're going to fix a certain window to be fully ones. And the idea, the idea, the idea then is we need to spend however many zeros there are in that window changes in order for this to work. So let's say there are x zeros in the initial LR, then obviously you need to spend like x changes in order to get this thing to be fixed to be completely one. So this is just a little detail, like you can spend x changes maybe just to click x changes. So what we have left, what we have left is q minus x. So again, this might seem like the problem is getting more difficult. No, it's the same idea. It's the same idea that the reason why I'm fixing L1 is because I'm saying that when L1 is fixed and it's bound, it's bound from 1 to n, then I don't have to worry about like maximizing one, but then it minimizes the other. No, one is already fixed. So now I can fully put my attention on L0. And the way you fix L1 is you can just choose a segment that is R minus L1, or this should be 0. That is like this long, and when you do that, just apply the amount of changes to get this fully to be ones. And it can happen that this is not a possible, like it's not possible to have a segment of, like if you want to, let's say you're trying length L, it's not possible to have a segment of length L. It could be possible. That's more like implementation details. It can be very possible, and then you just like omit it and you just don't think about it, right? So now what do we have left to do? We're trying to maximize. So now we need to think about like sort of like regather and think about what we're trying to do. What we're trying to do now is we only want to look at now the prefix here. The only thing, because this part, the middle part of the segment is already fixed. So there's no point of looking at that, right? So the only thing we want to worry about is this prefix here. Okay, this prefix, right? This is clearly a prefix, and we only want to worry about this suffix here. That's what we're going to worry about. And in this prefix and this suffix, so literally this is what we're going to have to do. Let's rigorously write where we're going. And the reason why, like sometimes like it's simple as just asking yourself, okay, what do we need to do? Like writing that very clearly, that will motivate like this, because this is gonna motivate the dynamic programming. So what we need to do now, what we need to do to, to be able to do is in a given prefix find the maximum L0 given you have let's just say a certain amount of changes. So the general problem is find the maximum L0 within a given. For simplicity, when we talk about the prefixes, suffixes and prefixes are like mirrored, like they're the same idea. It's just mirrored. Right? It's backward proofs. So for simplicity, we'll focus on prefix question, uh, suffix essentially. This is the general problem because this is what we now need to know how to be able to do. Is because if we're fixing a segment of things to be completely ones, then basically, um, in both the prefix and suffix, but basically the general problem we're now solving is that can you give to me the maximum L0 given that you have at most k changes? So what does this motivate? This sort of motivates dynamic programming. Um, the motivation behind this is just like recognition because this is what we want by definition. So we let prefix ij, be the maximum L0, and let's just rigorously define this: the maximum contiguous length of zeros um, within ending no later or contained within the I prefix, ending no later than I. So we let because this is what ultimately you don't have to think about this. This is ultimately what we want to find. Um, and we have applied no more than J changes. This is ultimately what we want to do because our idea. This is the general problem that we reduce it down. Find the maximum L0 within a given prefix or suffix, given that you have k changes. So what we can do is we can say we let. I'm trying to find a way to like logically uh, make this not contrived. So what we'll do is we let prefix ij be the maximum L0 contained within the I prefix, and we applied no more than j changes. So this obviously this prefix with this state of I is important, like it's obvious, like, but j is also important because we need to make sure that we have a solution such that we've applied no more than j changes, right? Um, that's pretty obvious. So that's what we're going to do in our state. And basically, we know that we know. So okay, we know that prefix and k will solve the problem. Because basically, what I'm saying is that considering all substrings in the entire string, and we have no more than k changes, will solve the general problem. Like that's obvious, right? And so that's why we're considering the state because we need to know um, that will solve the general problem. Right? We have a new general problem that we're focusing on, and so then we can just say, okay, that's what we need to do, and then the state is obviously that. So then, how do we transition? It's actually not too bad to transition. It takes a little bit of thinking, but like it's definitely possible. So prefix ij, we want to find the transition now. All we have to do is transition, and this problem is solved. So it's pretty much solved, and I'll just like explain the code. So as long as we know how to do this, then the problem is actually solved. So how do we transition? Okay, so when you're transitioning, right? Like dynamic programming, right? I haven't even had like rigorous training on DP yet. I've like done problems, but like this still seems like this should be like this idea of like, at this point you think about what have you already computed before, because that's the whole point of transitioning. You're trying to abuse previous states to get, let me not say abuse, but you're trying to use previous states, right? So the idea is that we've computed I minus one, we've computed the table, so we've computed we've computed the table for I minus one. So essentially we know how to solve this problem. Like, we know how to solve this problem for a shorter prefix by I minus one. We know how to consider all possible at this point, right? And then we know how to consider j, right? So this obviously, this is representing, again, this is the maximum L0. So the idea is that now, let me write this. So let's say we have some prefix I, length. Let's say this is length I. Okay, so let's say this is I. Or I kind of want to make sure I'm doing this. Okay, I minus one, I. So we want to find the maximum L0 in this segment. So one possible candidate for the maximum answer is, it could be, this is one possible candidate. And this is just, you just write this straight. It's the idea that you can just basically, because you can ignore the addition of the new character and just say, okay, what if we just consider this string, then what is the max? Okay, let's just consider all substrings here, and that will consider a lot of them, and then we'll just take the one that has the maximum one to consider as our new state. So that's basically, because there's really two cases, right? Two really general cases, right? Either the new character actually matters or it doesn't, right? If it doesn't matter, then you obviously just then the problem is just solving prefix I minus one j, and then you've already computed that, so you're considering the short, a little bit shorter prefix, and right. But now it might actually matter. So that's the case. Prefix it might actually matter. Um, okay, so okay, so if it doesn't, if it does matter, then we have to consider I, like either either I matters or it doesn't. If it doesn't matter, then obviously we could just remove it and then we have solved the problem. Um, if it does matter, then we know that we have to consider that prefix and wait. Am I trolling? Okay. I see. Okay. Let prefix be the maximum L0. Okay. So if it matters, then because you have to think about what you've computed before, right? Because you're trying to find candidates for L0. So another candidate is that this character might actually matter, and you can now at this point, if this character matters, you can consider all substrings with length with changes no more than with changes of j minus one or left, right? Yeah. That's it, because because you've obviously, like, at that point you've obviously computed j minus one for I, and so um, we're breaking this into general cases. It matters. It doesn't. But if it does matter, then since you've already computed j minus one, since you're trying to find candidate substrings that could possibly beat the L0, then things to also consider is the fact that, like, you could use the last character and you could just like solve the problem, given that you have no more than j minus one changes. But then it gets a little bit tricky because the last thing that you have to also think about is you have to think about this in the sense that, like, um, the strings can now end on I. Like now you have to think about substrings that end on I and use no more than j changes, or basically use exactly j changes. use exactly j changes. Because we've already considered strings that end on like I. This is implying that the character actually matters now. Um, we've, we've already considered that in the prefix I minus j minus one, and we've also considered the fact that they use no more than j minus one changes. But this is prefix ij represents no more than j changes. So now when we're considering the last character, we have to look at the thing that we're now missing are the things that use exactly j changes. So we can sort of say exactly, and then we can exactly. We want to use exactly j changes. Exactly. So exactly at ij represents a substring that ends on I exactly and uses exactly j changes, because that's what we're missing now, right? Because I've really thought about the things that if it doesn't matter, right? Now, but if it does matter, we know how to get if it ends on I, if it uses like j minus one, that encompasses everything. But the thing that we're missing from that is we're missing the fact that it uses exactly j changes, and so then we can just have this quantity called exactly, and so then the question now raises, how do we calculate exactly ij? This is kind of intense again. So this is actually not as bad as you think it is. This is pretty easy. What you have to think about is so again. Let's actually like be rigorous in the definition. Definitely for DP. Definitely know what your state is like, and that like so you can stay focused. So basically, this string has to end on I and has to use exactly j changes. So the way we can get this is that if it has to use exactly j changes, either we can force the string. Um, this is good. Oh, okay. Either if it has to end on I, this means that and we're trying to maximize the L0 again. Okay, we have to also remind ourselves what we're doing. We're trying to maximize the L0. So either if it ends on zero, so if s of I, the current character, right? If this ends on zero, then then this is equal to I guess let me just try to say it. So this ends on zero, then we don't need to change anything, and we can just use the last one, like exactly I minus one j, and then take that length and just add one, right? Yeah, exactly, right? Because we know it can end on, yeah, exactly. And then if it ends on one, if it ends on one, then we have to use a change so that this is L0, right? We have to use a change, and so if we have to use a change, then we have to find the maximum one uh, that ended on I minus one that used exactly j minus one changes, because we have to use a change, and then we would add one. And this is like a little bit of some details that you have to think about in the DP. It's a little bit annoying, but the general idea you see it, right? This is what you would have to do, and that's how you would find it. Like if j minus one is on a bounds, this here going up to exactly right there's zero. Like it has to be one because you can't change it, so the answer is gonna be zero. So just don't update it. So it is that like if the character is already a zero, then you can just get the last state that ends on minus one, just add one. If it is one, then it means you have to change it. So if you have to change it, then you have to like then you won't you can then basically look at the longest zero that ended on I minus one, and then use exactly j minus one changes, and then use that change again, and then that would be plus one. And basically that's it. So now we know how to find this quantity. And by symmetry, suffix ij can be calculated with this algorithm. So now we know how to find, now we know how to solve the general problem. So let's remind ourselves, what did we need to do? Okay, well, if we fix the number in this problem, if we fix the number of ones, then we know we have k minus x changes. So then all we have to consider is the maximum of prefix. Um, so the idea is that this represents like contained within this prefix. So the prefix is obviously all minus one contained with this prefix, and you can use no more than k minus x changes. That's why you need this state of because you can't just know only for k. That's why we have the state of like um prefix ij, because we're gonna have changes left over, and we're gonna need to know how to solve those subproblems. So that's why the state is extremely motivated behind this setup, right? But it's gonna be maximum prefix l minus one, k minus x, and obviously suffix r plus one, k minus x. We have this many changes, and these are like in our suffixes. And if we can find the maximum of those, then we know this is gonna be the maximum L0, and that problem would be maximized. And then it's very after you know how to solve do the L0 L1 case, it's pretty much the same thing. Like the solution to like handle the queries is very obvious. So go look at the code. Um, I didn't actually code exactly because I populated a prefix with exactly, like I populated it with exactly. So maybe that's not really as clear. But yeah, you can just sort of like, I would recommend coding this idea yourself. But this is pretty much the code. It's not too bad. Um, I did debug a little bit because I was trolling. But yeah, for the queries, I guess a little bit more details for like fixing ones. So you try to fix every L1, and then you try to say how many zeros are in this segment, which is just standard prefix sums. And if that is over k, that means you can't make too many operations. But if it isn't, then every time um, every time you can do this, then just you can map the length of that segment, like the length of the L1 value. You can map that L1 value with the L0. Because for every LR segment, you're trying to fix the amount of ones. Then you can map that length, that L1 value, to the L0 value. And you can just find the max for each possible L1 value. You can find the maximum L0 value because you're fixing it. So you'll be able to find the maximum L0 value. And then what you can do here is you can just check if for each A, just check just to find the maximum L1 value, and or just find or go through every single L1 value, and that fixed L1 of L1 will give you the L0 value. You do 8 times that, and then plus L1 answer. So you think there's a little bit of like details and nuances to think about after that, but it's totally possible. You sort of just have to lock in, and then you'll be fine. You'll be okay. But I think the main idea though that I really want to focus on, that I really wanted to emphasize on this problem, again, we can delve into the nuances more. It's sort of a little bit overwhelming, but the idea is this setup. This setup motivates the entire solution. It's the idea that you should fix L1 because fixing L1 allows you to only worry about L0. And then obviously this prefix suffix, right? Then you're at, now then obviously this dynamic programming state is very obvious because now you're reducing the amount of changes, so you need to know how to solve that subproblem. And you're also reducing the prefix. So like the dynamic, it's very motivated. It's not some contrived thing, but I think it all comes from this idea that you fix the segment to be all ones, so you can sort of have some clarity on the problem. So yeah, this is definitely a difficult question, but it's doable with that sort of mindset. So that will be it.